Welcome to section 4 of Unit 3, and in this session we'll be looking at factors that affect reaction rate. By the end of the session, you should be able to state and explain the factors that affect reaction rate. We'll be looking at nature of reactant, concentration of reactant, temperature, and then catalyst. And also, you should be able to state and explain what we mean by the collision theory. In chemical reactions, bonds are usually broken. So the rate of the reaction should therefore depend on the specific type of bonds that are involved in that particular reaction. If you take the reduction of permanganate in acidic solution by ferrous ion, and usually that reaction is instantaneous, the permanganate cannot disappear as fast as ferrous solution is added. The opposite is not the same. The reduction of permanganate, the permanganate ion in acidic solutions such as oxalic acid is not the same. That is because the oxalic bonds are organic, and in other words, solvent is an organic solvent, and the bonds are strong. So the bonds are not easily broken down, and because of that, it limits the reaction rate. If you take concentration, usually it is found that the rate of homogeneous chemical reaction depends on the concentration of the reactant. So increasing the concentration of one or more reactants will often increase the rate of the reaction. And this is actually true. It occurs because a higher concentration of reactant would lead to more collisions of that reactant in specific time period. So as more collisions occur, the rate of the reaction also increases. Quantitatively, the reaction is proportional to concentration, and therefore any change in concentration affects the reaction rate. Now with temperature, everyday experience tells us that the rate of a chemical reaction increases with increasing temperature. For example, most foods last longer when stored in a freezer but spoils quickly at room temperature. So an increase in temperature will raise the average kinetic energy of the reactant molecules. Therefore, a greater proportion of molecules will have the minimum energy necessary for an effective collision. And remember, it's not every collision that leads to a reaction. Usually, those collisions, or what we call the effective collisions, will lead to product formation. And these effective collisions is as a result of the kinetic energy. So molecules or collisions that have higher kinetic energy equivalent to the activation energy of the reaction will result into the formation of product. So not all collisions would definitely lead to product formation. Only effective collisions having an energy equivalent to that of the activation energy will lead to uh, uh, what we call product formation. Now, if you look at this particular diagram, you realize that this is at lower temperature. This is where the reaction should actually take place. However, when the temperature increases, then you realize that it increases the kinetic energy, which lower the activation energy for the reaction to take place. So basically, temperature and reaction rate, we have the effect of temperature on the kinetic energy distribution of molecules in a sample. And this is a typical diagram illustrating that at a higher temperature, this is where at lower temperature, this is where the reaction would have occurred. At higher temperature, this is where the reaction would have occurred. Now, a catalyst is a substance that accelerates a reaction by participating in it without being consumed. So, a catalyst provides an alternative reaction pathway to obtain the product. However, they do not get consumed in the reaction process. Now, one major use of catalysts are in the biochemical reactions, biochemical reaction pathways, which are very necessary, especially in the human several pathways that we talk about in biochemistry. So now when we talk about the collision theory explains why different reactions occur at different rates and suggests ways to change the rate of a reaction. The collision theory states that for a chemical reaction to occur, the reacting particles must collide with one another. The rate of the reaction depends on the frequency of the collisions, and the theory also tells us that reactant particles often collide without reacting sometimes. So for collisions to be successful, reactant particles must one, collide with sufficient energy and with the proper orientation. They must react, or they must collide, and they must collide, or if they will do that, then they must collide with sufficient energy. When they collide with sufficient energy, then they must do that with the proper orientation. So this is a typical representation of the collision chain: before collision, collision, and after collision.